Hi everybody, welcome to this video. This video marks the beginning of chapter 14, which is all focused on chemical kinetics. In this word kinetics, we've heard of kinetic energy before. Remember, kinetic energy is energy of movement. Kinesiology is the study of movement in humans. So chemical kinetics, we are thinking about the movement of molecules from one to another. We're going to talk about chemical reactions where one molecule becomes another and the speed at which that occurs. So we'll talk about reaction rates on this next slide here. Reaction rates, and then a bunch of different factors that influence reaction rate and how we can study those in chemistry. So we will get started. But on this first page, let me describe this first. There are two images. One is of a match that's burning, and one is a piece of iron that is starting to rust. So these are both chemical reactions. Rusting is a chemical reaction where iron and oxygen react together and form iron oxide. And lighting a match is a chemical reaction. We're seeing the matchstick burn. Lighting that match and burning in that chemical reaction, that's a really fast reaction. It has a fast reaction rate. Something forming rust takes time. So this is a slower reaction. So two chemical reactions shown here. One has a much lower rate than the other. And so we'll describe these different types of reaction rates. Okay, so this first section is just an overview of reaction rates. So we'll express reaction rates in relation to stoichiometry, and we'll get to really what that all means. Put Roadrunner on here on this page. He's a fast one. Okay, so reaction rate is defined as the change in concentration of a reactant or product per unit of time. We're going to use letters to describe reactants and products, but a reactant, remember, is something that you start with for a chemical reaction, and the reactant forms products, and there's some rate at which that occurs. So rate, change in concentration of a reactant or a product. We can write a reaction rate in relation to the reactant or the product per unit of time. So that's how we get to reaction rate. The concentration unit, so we talked about different concentration units in class. That can vary, and the time that's used, the unit of time that's used in a reaction rate can vary depending on the reaction. So for example, you can say a rate for a reaction is 0.3 moles per liter of a certain product per hour. So that product is generated and produced at a rate of 0.3 molar per hour. Or you can say that a reactant disappears at a rate of 0.001 millimoles per liter per hour, or per second. So this is concentration and this is time. Concentration and time. Now, when we have really slow rates, typical units for reaction rates in general are molarity per second. And of course, this is if we're describing in terms of molarity. So molarity per second is a typical reaction rate. But if you have a really slow reaction, usually the time unit will change. So it could be molarity per minute or molarity per hour for really, really slow reactions. Let's use H for chemistry. Because that molarity is changing at a much slower rate. So instead of molarity per second, we'd have molarity per minute and molarity per hour for really slow. So you'll see these types of units used for reaction rates. Some concentration unit divided by a time. On the next slide here, we have an example reaction right here. So we're saying that the reactant we're labeling as A and the product we're labeling as B. So still reactant to product, A is the reactant, B is the product. And so the rate of this reaction, now in this equation, A and B are in a 1-to-1 molar ratio. So A to B reactant to product. So that means at the same rate that A is being used up, B is being created. So the rate change in concentration over change in time, we'll use delta to represent change. So this triangle here, delta concentration over delta lowercase t for time. And remember that these brackets here now, those also symbolize concentration. So the rate of this reaction is equal to the negative change in concentration of A over time. Concentration of A is decreasing. So the concentration of A at two different time points, the second time with more time will be lower. And then B is increasing. And so we can say the concentration is equal to the loss of A or the generation of B over time. Here's another reaction. Now notice we have 2A to B. So now we have a 2-to-1 molar ratio. And these are the 2 and the 1, these are the coefficients in the balanced chemical reaction. So we have a 2-to-1 molar ratio of A to B, which means 2 molecules, or we can talk about this in terms of moles, of A disappear or are used up for every 1 molecule or mole of B that is generated. So that means that the rate of A disappearing is twice the rate of B being generated. And we can see the difference in this graph here where the red line for the concentration of A decreases at a faster rate than the concentration of B is increasing. And so that comes into play in the rate law, this rate equation, where for concentration of B, which has a molar ratio or a molar coefficient of 1, we can say the rate is equal to the change in concentration of B over the change in time. But we can't use the same equation for A as the previous slide because now A and B are not in a 1-to-1 molar ratio. So we have to say that the rate is half the change in concentration of A over change in time because A is decreasing at twice the rate that B is appearing. So we would have to have these two equations be equal to each other, change in A over delta T to delta B over delta T. We need a 1/2 in front of multiplied by delta A over delta T. So the molar ratio, the coefficients of the reactants that are part of a reaction influence the reaction rate. Let's look at another one where we have 2 products here. So A plus B or A goes to B plus 2C. So now we have two products, one reactant. A and B are in a 1 molar ratio. And then C has a 2-time molar ratio to both A and B. So this means for every 1 mole of A, two mole of C is produced. We can say for 1 mole of A, 1 mole of B is produced, or for 1 mole B produced, 2 moles C is produced. So we're just putting words to the molar ratio that's present in that given balanced equation. So A and B have a 1-to-1 molar ratio. C has a 2-to-1 molar ratio to both A and B. And so we can write the rate as the decrease in the concentration of A over time. We can also write the rate law in terms of B and in terms of C. B is generated with 1 mole of B for every 1 mole of A used. So we can say the rate is equal to the change in concentration of B over time, change in time. Because C is generated at a rate that is twice as fast as B, then if we're writing the rate law in terms of C, we need that 1/2 there. So 1/2 times change in concentration of C over change in time. We're going to have other ways to determine rate laws, and we'll get to that in this chapter. But for now, just to put this into context, perhaps you are a scientist, which could be you, are performing a chemical reaction. You want to calculate the speed at which that reaction occurs. And to do so, you measure the concentration of one product over time. As long as you know the concentration of one product, or even if you choose the reactant, that's fine, and you know the balanced chemical equation, then you can calculate the rate for the entire reaction. So that's why we write rate laws in terms of individual reactants or products. So again, rate is the change in concentration of a product or reactant over the change in time, and the stoichiometric ratio, or the coefficients in a balanced chemical equation, will influence the rate for different reactions. Now, there are other factors that can alter a reaction rate. One is the particle size of solid reactants. So I'll briefly explain this one here. If you are reacting two solids together and you have two large particles, so large particle size, there is fewer places where those two particles can interact, and they must interact for a reaction to occur. For a chemical reaction to occur between any two molecules, those two molecules have to collide with one another. So if you have really large particle sizes, there's fewer spaces where the two different chemicals can interact. But if you imagine taking like a large particle and then in a mortar and pestle grinding that up to be really small and mixing in another chemical doing the same, there's a lot more locations where the two solids can interact. And so it's easier and faster for a reaction to occur when you have smaller particle sizes when we're talking about solid reactants. That could also be the case if you're adding a solid into a liquid, Having smaller particles means more molecules can interact with a liquid and a reaction can occur. 4 other factors. One is the concentration of reactants. So we saw that the rate law is concentration of a reactant or product over time. So if you have a higher concentration of reactants, that can influence the rate of the reaction. And again, another way to think about this is if, let's say we're doing a reaction in liquid, if you have very dilute reactants, they are presumably dissolved in the liquid, floating around, and the chances of them colliding with another reactant that's also added to solution is low. So let's put a picture to this. So let's say this is our beaker. The liquid or the solvent is not what is reacting. We're going to add, let's say, this reactant in this color, and I'll do orange, another reactant. So if you have a low concentration, there is a lower chance that a blue molecule and an orange molecule will collide together. But if we have a high concentration, everything is closer together and it's more likely that a reaction will occur because it's more likely that 2 molecules that will react will collide with each other. Next is the temperature. So, like I said, collisions have to occur for a reaction to occur. If you increase the temperature, then the movement of these particles is faster, and so they're more likely to collide with another. The nature of reactants. So if a reactant is stable or unstable, can influence reaction rate. Stable meaning lower energy, unstable meaning higher energy. Something that's unstable is more likely to react. It's higher energy and available to be reacted with. And then the presence of a catalyst can influence reaction rate. We'll explain that one when we get to that section of this chapter. But generally, a catalyst is something that can be used to speed up the reaction rate, but it's not actually part of the reaction, and it's always regenerated at the end of the reaction. So the last 4 here, not the particle size, but the remaining, we have a section dedicated to each one. So we'll go into more detail for each of these. But I've got 2 example reactions here. The first is the decomposition of nitroglycerin. This is an explosive. This is a very, very fast reaction, and that's what makes it so explosive. It also releases energy at a fast rate. It produces all of these gases. So look, we start with a liquid, and then that reacts and explodes into a bunch of gases and releases energy, and so that is a very fast reaction, and that's why it's explosive. A reaction with limestone with water and carbon dioxide is very slow. This is what forms the stalagmites and stalactites in caves, right? That if you're in a cave, they can form these things. I don't have a better way to draw that or describe it, but that's a very slow reaction. It takes time for the limestone to react with H2O and CO2. So again, 2 examples of a fast and slow reaction. All right, if you need to take a break from watching, now's a good time because we are going to the next section. And we'll just go ahead and get started with this. So now we're looking at reaction rates and concentration. So we're still going to be describing rate laws and different ways to determine the rate law of a chemical reaction. And so let's go ahead and do that. Okay, so there are 2 methods to measure a reaction rate. We talked about potential rate laws in the first section, but now if we're thinking about in a lab, how you will measure a rate, or how you can measure reaction rates for different reactions. So you could calculate the average rate by measuring the concentration of a reactant or product at 2 times and then divide the change in concentration by the change of time. So you get change in concentration divided by change in time. So that's possible. You could also calculate the instantaneous rate by finding the slope of a tangent line to the concentration versus time graph. So this is if you're taking a lot of measurements of concentration over time, and then you can calculate the rate at a certain time. This is often used by chemists to calculate the initial reaction rate. So when a reaction starts, what that rate is. And in most cases, remember the rate is affected by the concentration of reactants. As a reaction occurs, the concentration of the reactants is decreasing. So the rate often decreases over time as reactants are decreasing, as the concentration of reactants decrease. Okay, so let's do an example here. We'll do method 1, measuring change in concentration over time, and method 2, looking for a tangent line. So let's say we've got this 1-to-1 molar ratio, reactant A forming product B. And our goal is to calculate the average reaction rate for this reaction between 10 seconds and 30 seconds. So we'll use the values in this row and the values in this row. We have concentration of B measured, so we'll use rate is equal to the change in concentration of B over change in time. This is positive because B is being generated and we don't need a 1/2 or anything because we have a 1-to-1 molar ratio from A to B. So to find the change in concentration of B, we would take the concentration of B at 30 seconds and subtract the concentration of B at 10 seconds and divide by change in time, which is 30 seconds minus 10 seconds. So putting values, the concentration of B at 30 seconds is 0.0650 molar. Concentration of B at 10 seconds, 0.0295 molar. And then divide by change in time, 30 minus 10, 20 seconds. So the average reaction rate between 10 and 30 seconds for this reaction is 0.00178 molar per second. So that's method 1. We've are provided measurements of the concentration of B at different time points, and we can use that to calculate average rate. Method 2, calculating instantaneous rate, well, you would have to use those values that you generate for concentration of B at different times, plot the data points on a graph, so we have time versus concentration, and then to calculate the instantaneous rate at 20 seconds, you've got to take a tangent line at 20 seconds. So approximately like that, tangent to the curve, and measure the slope of that line. And that would give you the instantaneous rate at 20 seconds. So the next slide, we have more space to do that. So like I said, method 2, plot your data points, draw a tangent line at whatever time you're looking to calculate the instantaneous rate. Let's see, do I have the line here? I do. And then use XY points to calculate the slope. So we are going to use at 40 seconds the concentration is 0.0850 molar. So that's one XY point that we will use. And then we'll use 0 seconds, so the beginning and the end of this line for what we've graphed here, which is at 0 seconds, concentration is 0.0160 molar. All right, so using those two, we can find the slope, which is y2 minus y1 divided by x2 minus x1. So this is x1, y1, or sorry, x2 and y2. This is x1 and y1, or x and y points. So plugging values into this equation, we have 0.0850 molar minus 0.0160 molar divided by 40 seconds minus 0 seconds. So the slope of the line here is 0.00173 molarity per second. So this is the instantaneous rate at 20 seconds for this reaction. Now notice that this instantaneous rate is slightly different from the average rate that we calculated here. They're really similar, but they're not exactly the same. Instantaneous rate is helpful if you are looking for the rate at a specific time, but that rate is going to vary depending on the time that is chosen because this tangent line has different slopes. This reaction, the red curved line here is showing the concentration of B at different time points. But notice that the slope of that line changes as time goes on, and that's because usually reaction rate decreases as reactants decrease. So we're losing reactant, we're losing A that can produce a product, so the product will be generated at a slower rate. So that actually makes these two methods only accurate at specific time points. But we can write rate laws to accommodate for changing rates with changing concentration of reactants. We use the rate constant, which is lowercase k. And we use a term for the concentration of each reactant raised to the power of its order. So a lot of new concepts here. So for a reaction where capital A, that is the reactant, and capital B is another reactant in this case, that is forming products. Lowercase a and lowercase b are the coefficients of reactant A and B in the balanced chemical equation. So we're using these lowercase letters to represent coefficients. We can write the rate in terms of A as having, since this is a reactant, we write it as negative 1 over its coefficient times the change in concentration of A over change in time. So that's one way to write the reactant law, or the rate law. We could also write it as 1 over lowercase b times the concentration of capital B over change in time. Another way, which is what we'll use mostly in this chapter, is having the concentration, leave a little space in the beginning, concentration of a reactant, A, raised to a power, we're using a letter because that power can change, times the concentration of B raised to another power, and then all of that multiplied by the rate constant, lowercase k. So this, taking these two reactants and writing this rate law with the variables present here can always work. We will determine the values of N and M and K experimentally, or they will be provided. We'll go through examples to put this into context. Okay, so K is the rate constant, which is determined experimentally. N and M we call the reaction order, also determined experimentally. Often the reaction order is 0, 1, or 2. And what these exponents account for is the change in rate for the change in concentration of reactants. And then we can describe the orders of the rate based on those exponents. So if n equals 1, and we'll say m equals 2, then we'd say this reaction is first order with respect to A and second order with respect to B. And overall, the reaction is third order. So lots of new information on this page. Next slide, we'll talk more about these reaction orders. This graph here, we have time versus concentration. We're looking at a reaction that has one reactant, A, forming some product. And this graph shows the reaction, or the concentration of A for 3 different reaction orders. So this is not for one chemical reaction. We're saying if N equals 0, we have that red line. If N equals 1, it's first order, we have that dark blue line. And then if N equals 2, we have a second order reaction, which is the light blue. So if something is 0 order, if that concentration is raised to a power of 0, that means that over time, there's no change in the rate of disappearance of A, even though the reactant concentration is decreasing. So the concentration of A decreases at the same rate over time. For first and second order reactions, these show a slowing of the reaction rate. Because the reactant is disappearing more slowly as the reactant is used up. So the second order line, or first order line, let's look at that one. It decreases at a certain slope and then it starts to level out. So the rate at which A is decreasing is changing over time. It's slowing over time. And then the second order reaction rate slows in a more pronounced manner as the reactant concentration decreases. Okay, let's look at an example here. We'll do a few learning checks. So let's say we have a reaction. A and B are reactants, C and D are products. And the rate law is provided as the rate constant, K, times the concentration of A squared times the concentration of B. From this rate law, we can complete the blanks in this bullet point here. First one is the rate is some order with respect to A and then what order with respect to B. Well, the coefficient tells us what that order is. So, not the coefficient, the exponent. So the exponent for A is 2. So the rate is second order with respect to A. And B is included in the rate law, so it has an exponent of 1. We usually don't write the exponent of 1, but if that reactant is included in the rate law, then you can assume that coefficient is 1, and it is first order with respect to B. If something had a 0 order, like if B was 0 order, it just would not be part of the rate law, but you would still know it's a reactant based on the chemical equation. Okay, now second bullet point, or third, I guess. At a certain concentration of A and B, the reaction has an initial rate of 0.320 molarity per second. Calculate the new initial rate when the concentration of A is tripled and the concentration of B is doubled. So, for this question here, we have to consider the rate order for each reactant and the result of tripling the concentration of one and doubling the concentration of another. If we triple the concentration of A, so instead of A in this equation, we have 3A. Well, that 3 is squared, so this actually increases the reaction rate by 3 squared, which is 9. So this is concentration of A is tripled. This is the result of that. If we double concentration of B, that increases the rate by 2, because we're doubling, raised to the power of 1, because the reaction is first order with respect to B. So increases reaction rate by a factor of 2. We multiply in the reaction rate, we multiply A and B together, so the overall rate reaction rate increases by a factor of 9 times 2, which is 18. Another way to write this is to have a ratio where we have new rate to old rate. We have the same rate law, so let's write the old rate first. K, concentration of A squared, concentration of B. And then the new rate, we have 3 times the concentration of A squared times 2 times the concentration of B. We can cancel everything out except for 3 squared times 2, which is 18 over 1. So 18 times the original rate. So new rate is 18 times the old rate. So 18 times 0.320 molarity per second. The new rate is 5.76 molarity per second. So both increasing concentration of A and B increases the reaction rate, and it depends on the rate law to determine how this exactly impacts the reaction rate. All right, I will end this video here and we'll do more examples in the next video for chapter 14.